Our last speaker this year in that room is going to be Alex Crichton, who is a fan of the indie time travel movie Primer, but also is a member of the Rust core team and has been working on the Rust programming language for 5 years now. And he's going to talk to us about that language, giving a bit of an introduction. So let's welcome Alex Crichton.
All right, thank you everyone. I know everyone's probably a little bit tired after the final day now, so I'll probably keep this a little bit short, and I want to say that if you have any questions, please feel free to raise your hand at any point. This is very much engineered to be a talk, to be very interactive, ask questions, stop at any time. May not get through everything at that point, but it's all right. These slides are available online, and we'll be able to find them there. But so I always love to start off with the sense that I started working on Rust 5 years ago when it was effectively an entirely different language, back when we had garbage collection and a giant runtime and green threads and all this stuff. And so if you remember anything about that version of Rust, it's now entirely different. There is effectively nothing left other than the kind of the fn main, the actual hello world function. But in any case, to start off, I want to give you a bit of an idea about what Rust is and what Rust has to offer. So I'm assuming that many of you have not even heard of Rust before. This is your first introduction, or you saw my talk yesterday and you're like, I have no idea what this is and I want to learn more. So the first thing you'll find in Rust is the fact that it has very strong safety guarantees. This is no segfaults, no data races, and a very expressive type system to kind of add on to these safety guarantees with your own extra logic, with your own extra validation. And so this is kind of giving you that sense of security, that sense of comfortableness you'll find from Java or Ruby or JavaScript, kind of these languages that manage all this for you, and you very rarely deal with GDB or segfaults or weird production things that are difficult to debug. But on the other side, Rust also gives you this uncompromising performance, this performance you expect from C and C++, and we do this by not giving you a garbage collector. There is no runtime. When you're writing Rust code, it's kind of at the lowest layer. It's kind of running directly on the machine. We generate machine code. We generate normal executables, as you see in C and C++. And so you're kind of putting these both together, which is giving us this aspect of a confident, productive systems programming language. Now, the systems aspect here is very much the C and C++ and very low level, but the things to focus on are kind of this confidence and this productiveness, where this confidence is stemming from this lack of segfaults, these lack of data races, kind of all these guarantees that Rust is giving you. And then this productiveness is not only kind of the security you feel from this is now enabling you to do so much more, but there's this very active community, very active ecosystem, and I'll be talking a little bit more about that later, which is kind of adding to the effect of being very productive in Rust. And it's kind of a core tenet of what we focus on, which is not just the language, but also how you feel when you're working in the language, spanning all the way from your build system to the actual when you're running code on the machine. So some people kind of listen to this and they're like, oh, well, I don't really need safety. It just seems like eat your spinach. It just seems like this kind of chastising you. Your mom saying, oh, you should do that every morning. You should make sure you're safe every morning. But we like to think of this not so much as the kind of canonical eat your spinach where it's not a great thing to think about, but rather this Popeye superpower where you eat spinach and become super strong and you have this new superpower to work with. And one of the best ways that I find to articulate this is through an actual real story of discovering a bug in the Rust compiler. The Rust compiler is written in Rust, but I'll get into that later. So imagine you're kind of just this generic program. You have this thread of computation where somewhere along the way you'll kind of do some work, and then after that work is done, you'll update this shared data structure. This kind of big red rectangle is just some data structure on the side. You'll do some more work, and then you'll send some more updates to that, and finally you'll kind of get some result, and you'll print this out. So this is kind of just a general abstract program, but eventually you're like, okay, this is not actually fast enough. I want to shorten this runtime, and I want to add some threads. That's kind of one of the easiest ways to make my program faster. So we'll add a separate thread here, and then to actually communicate between this, we're going to be doing message passing. So we do a tiny bit of work, we send this message to the other thread, which will actually do some work. And then one thing we've noticed is that this data structure is now entirely owned by this separate thread. It's kind of this nice, well-contained data structure. We'll do that again a couple times. We'll kind of expand some more work. We'll share the load between these two threads. And overall, we got this great benefit by now when we actually receive the result, our runtime has now shortened and we have a much faster program at this point. And so this actually happened in the compiler where we added threads at some point to kind of shorten the execution here, and everything was great. So now we have a faster program, we're using threads, it's safe, everything works, and we kind of move along now. So we come down the road, we're 6 months later, at this point we've forgotten we had threads, we've forgotten we had this internal refactoring, all we know is our program is fast and we want to add a feature to it. So we'll come here, we have our current program, we have our message that we're going to send, and right now it's not quite good enough. So we have this struct event, which just has some data members. It currently has a key and a count, or just kind of some other various bits and pieces. But we want to add this field called intern string. We kind of want to add some more rich data to go across these threads. And this is when it gets scary. I don't know about you, but the scariest thing you can do as a programmer is to read code you wrote 6 months ago. So what's actually happening here is that we have this event that we're trying to send across strings, notably this intern string field. And if we go deep enough and we actually look at the internals of this intern string, what we're going to realize is that internally there's this reference counted string, this RC of string type. And the notable thing about this is that it's non-atomically reference counted, which effectively means that if we were to allow this, we're now going to have a data race. We're now going to have double freeze. We're going to have weird crashes, or it might not even crash at all. We're not really quite even sure what would happen at that point. And so this is kind of a really embodying the fact that you as a programmer forget what you've done before, you're forgetting the current architecture of the program, or you're brand new and you had no idea that there were threads behind here. And so when you actually try and do this in Rust, when you actually try and write down this intern string and then send that across a thread, the Rust compiler will immediately tell you this type cannot be sent across threads. It is not safe to send this across threads, and this program is rejected at compile time. And you can immediately start working around this. You can say, oh, well, I don't actually need to send an intern string. I just need to send the length of it or kind of some other aspect of that. So that's kind of a story of the safety aspect of Rust, but I want to give you a bit of an idea as well about the kind of low-level, zero-cost abstractions we have. This is the kind of performance at the C and C++ layer. So one of the greatest ways to show this in Rust is this abstraction of iterators, which is somewhat different than the C++ iterators. They're kind of a little more specific to Rust. Where so here we have a list of integers. We're going to call this zip function over on the iterator. So we'll take 2 iterators and make 1 iterator of pairs. We'll then just take each one and we'll multiply it together, and at the very end we'll actually sum it all up. So this is pretty readable. This is relatively easy to kind of see. We can kind of tack on some more iterator adapters here that we would like. But the key thing here is that Rust is kind of compiling all of this away. When you actually look at the x86 assembly generated, you can see this nice compact piece of code which is actually even vectorized. This is using SIMD instructions under the hood, which you didn't even explicitly ask for. And so this is kind of the LLVM compiler is what we actually use as a backend and has very, very advanced optimizations. And so this is showing how even though you're writing kind of this high-level, very closure-based, iterator-based, all these extra abstractions, they're all compiling away and melting away to the kind of the fastest machine code you would have otherwise written by hand. And not only are we enabling you to actually have kind of like in one compact code or in one compact piece, you can have kind of readable code for sequential SIMD-based execution, but we can also just change one line there from iter to par iter with some crates in the ecosystem, and immediately now we have a multi-core program, which is in parallel on many threads using work stealing, using SIMD, guaranteeing thread safety, and all these aspects kind of like with one tiny change. And this is kind of the expressive power of Rust, where we're enabling you to have these very small changes with zero cost overhead, giving you all these great benefits, and at the same time, you don't have to worry about data races. You don't have to worry about these seg faults. You don't have to worry about kind of all these problems you might otherwise be running into if you didn't have total knowledge of the entire program. And so the last thing I want to talk about here was the productive aspect, and this is probably best embodied with the crates.io application. And so this is a website very similar to npmjs.org or rubygems.org or PyPy, kind of like the Python package index. This is where you put Rust libraries to publish and for others to download as well. So at Rust 1.0, at the original release of the Rust project, we gave you a package manager called Cargo, which is kind of allowing you to very easily download from others' Rust crates and publish your own. And so this is a very effective way for growing the Rust ecosystem and for kind of immediately getting up and running with whatever packages you need for using HTTP, for having this parallel iteration, for whatever aspect you need. You'll probably find a crate on crates.io today. So all right. That's kind of a brief introduction to some of the benefits, some of the niceties, and kind of what you can expect from Rust. And so now I'm going to talk a little bit more about the language itself, kind of how we get this memory safety, how we actually build that up. I'll show you another feature of Rust called traits, which is kind of another aspect we start building a lot of safety on. Show you a little bit how that parallelism works and kind of how it leverages these two things, not quite as much as in-depth as yesterday. And then finally, talk a little bit about this unsafe aspect, how I'm saying safe Rust, but there's an asterisk next to it, where it's not quite, it's a little bit of a lie, but we'll see how it doesn't matter too much, or I'll explain it. And then finally, we'll talk about the community around Rust, specifically Rust and Firefox, which actually is exciting because it was just released yesterday. And then also some of the community processes of kind of how Rust is developed and how we can expect to see that. So all right, to start off, let's dive into this memory safety aspect. And so this is where we're going to be talking about not only are we getting this zero-cost abstractions from Rust, but we're also getting this memory safety and data race freedom. And kind of this is how we're building up in this confident productive systems programming. And so I want to dive into both of these at the same time to explain some of the pitfalls of how they work, or kind of how they could work, and then how they actually work in Rust. So to start off, let's talk about some zero-cost abstractions, kind of what you would expect from C++. So this is an example written in C++ where we'll start out with a vector strings in the stack, and we're just going to get a pointer to it. First thing we'll notice is that the vector itself is stored directly inline on the stack. This data, this length, the capacitor. So those fields are stored directly there, no layers of indirection or whatnot. The actual values on the heap are then stored sequentially as well. We have the first string, the second string, the third string, no extra stuff in there. And we'll notice that the strings themselves are just then containers of bytes, and then recursively have data length, capacity, and kind of just keeps on going around and around. Next up, we'll find that these element pointers, kind of these lightweight references in C++, are just raw pointers. They're just kind of straight pointers in memory. There's no extra metadata, there's no extra layers of abstraction here. It's just kind of pointing directly raw into memory. And the final thing we'll notice here about this zero-costness is this aspect of deterministic destruction, kind of where when we exit this function, we know precisely that we can deallocate this vector, free all the memory behind it, and we don't have to worry about any explicit free calls or leaking memory at that point. Now, so when I talk about memory safety as well, I also like to show this with C++. This is very similar to the example yesterday, where we'll start here again with our vector strings in the stack. We have our data, our length, and our capacity, and we'll start out by having a pointer into that. But then we're going to come down here, we're going to try and push some data onto this vector. We're kind of push some extra pieces here. But the problem is that we might have to reallocate this vector. If this length is equal to the capacity, we make some new data, we update our data pointer, and then crucially, we start forgetting this data. We start actually deallocating that. We start deallocating the previous chunk of memory, which then invalidates this pointer. We now have this dangling pointer pointing into freed memory, which means once we actually come around to kind of try and print it, that's undefined behavior. We can get a seg fault, we could work and discover it a year later, we could have effectively anything happening at this point. And so what I like to do here is to dig into what was actually happening and then why we actually want to prevent, how we can prevent this bug, but also many other bugs at the same time. And so the first ingredient we'll find here is this aspect of aliasing, where we have both the vector pointer and this element pointer are pointing to the same piece of data, but they didn't really quite know about each other. But in isolation, this is just fine. It's only when we add in this mutation, when we have this simultaneous act of updating one of the pointers while we forgot to update the other one as well. If we just had mutation, the vector itself was always internally consistent. And if we just had aliasing, nothing's actually changing, so it's totally fine. And so it's purely when we have this simultaneous act of both aliasing and mutation, which is when we start running into trouble. And these two ingredients are not just related to this bug, but actually most memory safety bugs start diving into one of these two factors happening at the same time. So most of Rust and all of the safety aspects I'm about to show you are fundamentally driven at preventing this, preventing simultaneous aliasing and mutation. So we'll start by having this kind of tabular category of kind of classifying these two concepts in Rust called ownership and borrowing, which I'll be talking about in a lot more detail. And we'll be seeing how they either allow aliasing or they allow mutation, but never both. And so the first thing we'll be talking about is this ownership value, kind of this own type, where we'll be seeing that it does allow mutation. It's signified with kind of this bear type T, and then has this ownership passing. And so ownership in Rust is very similar to the English word, or kind of just the natural language word of ownership, where you yourself can own some value. So I personally own this book. I now have a copy of this, and I can do whatever I like to it. Notably, if I have this book, I can actually decide to transfer it to someone else. So I can kind of pass off my book to someone else, and now they are the owner of this book. I have relinquished ownership. I can no longer touch it. I can no longer read it. I can't even modify it. So let's take a look at some code and kind of see how this actually works in Rust itself. First thing we'll do is we'll have this book, which we'll just say is a vector of strings in the stack as well. And first thing we'll notice is, just like C++, Rust will store these fields directly on the stack, this data, this length, and the capacity. Now we've also declared this with this mute keyword, which means that we're allowing this kind of edit permission. We can actually modify this book, and we're allowed to kind of touch that and do extra things with it. So we can actually come here and we can push some pages onto this book, and now we have some data on the heap saying, oh, we got our first page of the book, we got our first string, we got our second page of our book, and we can keep moving from there. So now is when things get interesting, where we start saying, all right, we want to publish our book, and we're going to transfer ownership from the main function to the publish function. You'll see here on the right-hand side that this vec type, there's no extra fluff here, there's no extra ampersands or symbols or anything, and so what that means is the publish function is taking the book by value, it's taking it by ownership. Similarly, on the caller side, we're not passing any extra fluff here, and so we're passing this by value. The main function is relinquishing ownership. It's passing ownership of the book over to the publish function. At runtime, the way this is implemented is we're going to push the book on the stack, which kind of makes a copy of each of its fields locally onto the stack for the publish function, and then we're going to forget about the copy in the main function. It has passed ownership, so it no longer has access to it. It no longer can access its fields. It is now someone else's problem at this point. We'll come over to the publish function and we'll start executing, and just like C++ before, once we get to the end, we now know that because publish is the sole owner of this piece of data, we can destroy it. So we can light the cell on fire and free all the memory and kind of free all the resources associated with that. This is the deterministic destruction aspect of Rust and of C++. Now you might be wondering, what happens if we try and republish our book? This is a move value at this point. So if we tried to actually touch it again, this would be a use after free. And so what the compiler does is it gives you a nice error saying this is a use after move. You are statically forbidden from touching variables which have been moved, from using any value which has been moved at that point, and you can only move it if you're actually the original owner. So this kind of builds up a story for memory management in Rust, which might seem like it could be a little manual at first, where you have any value when you create it, you are the original owner. Now, as the owner of a value, you can actually move it to someone else. So you can assign it to a new value, you can pass it to a new function, and then when the final owner actually returns, you'll then free it up. So you can say, this is the final owner, so no one else has references to this, and we'll kind of deallocate all that. Oh, that was something I forgot to mention, which is, again, that mutation and aliasing is what we're preventing. And as we're seeing with ownership, we're allowing mutation, but we do not have any aliasing. We'll only have one owner at any one point in time. The key thing, though, is that most of this ends up feeling invisible in Rust. You actually explicitly create a resource, but then movement is just assignment, deallocation is just forgetting about it and letting it go out of scope. You never actually do anything manually here. A lot of this just kind of feels invisible and kind of just ends up becoming very natural in Rust itself. So the next thing I want to talk about is the second pillar of Rust, which is borrowing. Now, borrowing is also very similar to kind of the natural language phrase of this, where you, as the owner of a piece of data, can kind of temporarily loan it out to someone else, but at any point in time, you can pull that back. Now, you still have access to the book, you are still the owner of the book, and you can still then have exclusive access at that point. There are two kinds of borrows, but I'm going to talk about each one in succession. The first one of which is a shared reference. This is denoted with this ampersand sigil out in front, and we'll notice that this will allow aliasing, but it will not allow mutation. So to start off, let's have a similar example from before, where we have our book on the stack, we push some pages onto it, but we're going to start here with this ampersand. So we have this ampersand vec on the right-hand side, and we have this ampersand on the left-hand side as well, where we're denoting that the caller, kind of the function publish, is taking a borrowed reference to the vector. And on the calling side, we're also creating a borrowed reference with this ampersand here, making this function, or this pointer p here. Now, one key aspect we were saying is that this allows aliasing, but not mutation. Oh, sorry. The pointer p here, just like C++, is kind of this lightweight reference, just kind of pointing directly on the stack, just pointing initially at the kind of the data member here. But because I was saying we allow aliasing and not mutation, while we have this shared reference, we have lost our edit permission. We no longer can actually mutate this book through the original value. So we'll come along here, we'll then call our publish function, we'll push a new pointer on the stack as the argument to this function, which is kind of this function book, and this is showing how we can have multiple aliases at any one point in time. This is kind of, we can create multiple shared references, and that's all fine, we don't have to worry about mutation or anything like that. We'll come along to publish, and when that finishes, we'll just pop the values back off the stack, and now we'll keep on executing, and this will execute it, or this will actually compile and continue running. So the interesting part here is to kind of dig into some cases of where this can go wrong and what is actually disallowed while you have a shared reference. So here we have a book. Because we declared it mutable, we can actually mutate it, push some pages onto it, do whatever we like to that. But here's when it starts to get interesting. So we're creating this borrow. We're having this local variable called r, which is a shared reference to this book. And what's actually happening is this has a lifetime associated with it. So it's valid for this kind of curly brace block. It's valid for this one block right here. So if we try to actually mutate the original book, the compiler will give us an error saying we cannot mutate while this book is borrowed. So because there is an active shared reference, we cannot mutate the original binding or mutate through the shared reference as well. So if we try and actually mutate the original shared reference, that's also disallowed, saying the compiler cannot access, or do not have access to this. Notably though, when we do reach the end of this block, once we've reached the final instruction, we say that, okay, the scope now ends, this R has gone out of scope, so the book is no longer borrowed. We kind of have this scoped access where we know that there's no active borrows here, meaning that this final call to push, this is actually allowed. The book is now mutable again, there are no active borrows, and as the owner of the book, you declared it mutable and you can do whatever you want to that. So this is also a little bit of an asterisk where we say that you typically can't mutate while you're shared. Most of Rust is around preventing this aliasing and this mutation at the same time, but there are some controlled circumstances we do allow that, but I won't go into too much detail here because it's a little bit more of the advanced Rust side of things. So the next thing I want to talk about is we saw shared references, but now the second kind of borrow in Rust is a mutable reference, which, as you might imagine, is allowing mutation, but not aliasing. And we'll see it was denoted with this ampersand mute. So on the caller side of things, in this edit function, we're going to have this ampersand mute vec of string, which says that I would like a mutable reference, and that would like to be able to mutate that as well. Similarly, on the caller side, we're going to pass in an ampersand mute, saying, oh, you can actually edit this function. You can actually now have a mutable reference. So just like with shared references, a mutable reference at runtime is represented with just this nice thin pointer, just pointing directly on the stack. But like with shared references, we're going to kind of limit our access in the original book variable itself. So with a shared reference, you couldn't mutate it, but also with a mutable reference, you cannot mutate through the original binding. So the variable book here, while the mutable reference is created, is not mutable, but you can mutate through the book itself. So when we call the edit function, we will actually be allowed to call the push function, which will give us a second page of the book. I mean, once we return, again, we have the reference that has gone out of scope, so there are no active references, and so the state of the own value has actually returned the original state, which means we have the edit permission, and we can grab whatever borrows we like. So we can run this function again, and actually we'll successfully push a new fourth page onto this book, and now we'll have a nice book to work with. So again, I want to go into a little bit more detail about how these references are working and what's kind of the error cases are. So like before, we have a book, we can push it because we declared it mutable, and here we declare a mutable reference to this book. And this is kind of the starting point for which we are gathering a mutable borrow on this book. Now I was saying that you are completely disallowed access. Not only can you not read it, you cannot mutate it. You can't do anything to the original binding of this book. So this is going to be an error saying that there is a mutable reference active, so you no longer have access to this. You no longer can actually mutate the original binding or even read it. However, we can mutate through the shared binding as we saw. This will actually be allowed where we can mutate the original book, which will then kind of go through our reference to actually mutate the final value. Now again, just like shared references, once this returns or kind of goes out of the scope, we know that the lifetime here has fallen out of the scope, which means that we actually can edit the book here at the very end. We can kind of do whatever we like. We can gather more, we can push more pages, we can take more shared references, we can take more mutable references, kind of all that good stuff. So I've been kind of saying this word lifetime here, which I want to kind of go into a little bit more detail about what that actually is. And it turns out that the compiler is automatically inferring a lifetime for every borrow that you create, both shared and mutable. And this is kind of like, in this example, at the very beginning of when you first have this ampersand book of 0, from that point on to when the actual variable R goes out of scope is the lifetime here. That's kind of the lifetime, the duration for which that is valid. Right now this is mostly syntactically, but you can kind of think of this over time as well, kind of while this code is executing, that is the lifetime of this reference. And so we actually give these things names. It's kind of this tick L, which is this notation in Rust for this is a lifetime. You'll typically find one-letter names that are all lowercase, but you can make them much longer as well. The compiler, again, is the one that's actually inferring this. So in this case, you can't actually name it. You can't write down tick L, but it's kind of what the compiler is doing internally, is figuring out some lifetime, figuring out some name, and then rationalizing that with all other shared references or mutable references in your program. So this is a case where you can use lifetimes to start connecting borrows together. So we can say that this same variable, that's kind of the same tick A, is both on the input, this vector v, and the output, this reference to a string. And what that's saying is that given borrowed contents to a list of strings, I'm now going to give you a borrowed content to the first string with the same lifetime. And so this is saying that this will actually compile because these end up all having the same lifetimes and everything remains borrowed here as well. But kind of this derived from, like we will derive a reference from v to actually return this. And it turns out that's a little wordy, so we don't actually require you to do that all the time. We have this thing called lifetime elision in Rust, which basically says that the first definition here and the second one are exactly the same. The compiler will infer this one without lifetimes is the exact same as the one with lifetimes, if you had otherwise written that. So one of the great things I always love to talk about with lifetimes and kind of the benefits of lifetimes is in contrast with an example of a C API. So this is an API you'll find in the libgit2 library, which is a C library written for managing Git repositories, kind of like dealing with Git commits, histories, merges, all that good stuff. And so the first thing we'll notice here is we have, okay, let's try and figure out what this memory management story is. We have a lot of pointers going on here. We'll read the documentation and it'll say that, okay, it returns a tree entry that is owned by the tree, but you don't have to free it and you just have to make sure you stop using it before you free the tree. And so this is kind of this key aspect of we didn't actually know how to use this. We didn't know if we passed in a tree, if we had to free that reference, if we have to, I still don't know where file name is coming from. This lossy information kind of sometimes is in documentation. Now, this is not a bad part about libgit2. Libgit2 is excellent, has excellent documentation, but it's more of a limitation of C where you have to go out of your way to actually learn about the lifetimes here, to actually learn about how you're supposed to manage this memory, who's supposed to free this memory, when you're supposed to stop using this memory. Whereas in Rust, you would typically have a signature that looks like this. We have this tick A again, which says that I am taking a borrow of myself, and I'm going to return to you a borrowed entry which has the same lifetime as myself. And so notably, this is kind of implying all this information that we had to read from C. So we're seeing that not only do we not have to free the tree entry being returned, but the compiler will automatically verify that I can't use the tree entry beyond the lifetime of the tree itself because it's borrowed. Because you've borrowed, you can't move it, you can't modify it, you can't mutate it. But the other great thing about the Rust signature is it's actually more expressive than the C signature or the C documentation. Because we still have the question about what is this file name? Are you storing this file name? Do I need to reallocate it? Is this declared as read-only, but is there some other alias in the program which is being mutated? We're not actually quite sure what's happening. Are you starting a thread? Do I need to keep it actually alive for much longer? When all of this information is given for free in Rust. So we have here there's no lifetime annotation on this ampersand stir, so it's kind of this anonymous lifetime that you can't work with, which notably means that it's borrowed, so no one can mutate it. Kind of Rust guarantees that while you have a borrow, no one will be modifying the underlying contents. You know that because it's this anonymous lifetime, or I didn't name it, it doesn't escape. So this function cannot store a reference to this variable. It cannot kind of squirrel this away and you have to worry about that later. And while it's running, no one's modifying and kind of all that good stuff. So this is a great example of how these questions you have in C, these questions you have all these typical APIs where you have to really dig into documentation or sometimes read the source code just to figure out what's going on. In Rust, you just get that by reading the signature. And just by looking at the signature, you know exactly what's going on. We know that it's either mutable or not. We know the lifetimes of what's being returned, how to manage these resources. It's kind of just all there given for you automatically. So all right. That's enough about ownership and borrowing, and so I want to transition now to a second language feature which we also use a lot for safety called traits. Now traits in Rust are very similar to interfaces you'll find in languages like Java or type classes in Haskell if you're familiar with it. It's basically a group of a little bit of functionality that can be attached to a type. And so I want to show you an example here of actually implementing a trait for one of the standard types. And this is kind of actually a nice aspect of Rust, which is you can create a trait for yourself and then implement it for existing types, kind of like types in the standard library or integers or primitives. So we'll start out by having this trait called clone. And this is actually in the standard library, but we'll pretend that we have a nice local copy of this that we're working with. So the traits themselves will be implemented on particular types, which we'll see in a second. And this is kind of the collection of functionality, where in this trait we'll have one method called clone. It takes a reference to myself, which is the receiver of this actual method call, and then returns this capital S self value, which is saying I will return a new version of myself, kind of the type that this is being implemented for. It's this placeholder. So we take a look at this vec type we've been looking at with. This is kind of the list, the growable list, the growable vectors you'll find in Rust. And we'll start off by saying, okay, we'll have, we're implementing this for vectors, notably with this t::clone here, which is showing that for any list which has clonable items, I can now also clone that list and create a new copy of it. And this is typically when you find traits like this, they're kind of implemented recursively, where I'll kind of implement the trait for the outer type if all my generic type parameters internally also implement that type. So the first thing we'll do in this implementation is we'll create a vector. We'll kind of just make a new vector on the stack. We'll then iterate over it with this for loop, and this elem type will have just kind of a pointer into the vector for each element that we're iterating over. We'll recursively call the clone method, which we've given by this trait bound at the top. This kind of t::clone means that now this type is clonable, so given &t, we can create a new t. And then finally, we'll actually return this value at the very end. So another thing that's important to know about traits is that they're not quite, or they have so they're different than C++ in the sense that you check this definition only once. So we're type checking this as you wrote it, and kind of as you compile this one piece of code, we'll say that, okay, we know you can actually call elem.clone very importantly because you gave it a clone bound. There's nothing else you can do with that other than move the value around and drop it. That's pretty much it. Or kind of like basically let it go out of scope. Differently, or similarly to C++ though, we also have a monomorphized aspect here, where for every time you call this clone function, you're going to create a new copy in the machine code. So if you have a vector of strings and call clone, if you have a vector of integers and call clone, those are two separate copies of machine code, kind of hand optimized for just that one particular type. So naturally this gives us this kind of that zero cost performance, kind of as if you wrote it for just those types. But this of course has the similar problems to C++ in terms of code bloat if you write that too much. And so there's some ways to work around that and some knobs to tweak there, but I won't go too much into those here. So the other aspect of traits which we tend to use are these things called marker traits, where a marker trait doesn't actually have any functionality inside of it. It just kind of represents a property of a type. So here we have this trait send and this trait copy, which in Rust they mean that this is safe to send across threads, or it's safe to memcopy. It's kind of safe to just create new versions of this all over the place. And I already talked about send in terms of being safe and that RC type was not safe, but we will see that things like strings, things like integers, these are all safe to send across threads. It's totally fine. The string type is backed by heap allocation, but it's safe to allocate memory on one thread and deallocate it on another thread. That's kind of how allocators work. We also saw, though, that RC of string, because it's not atomically reference counted, is not safe to send across threads. So this type will not be implemented with the send trait, and we'll say that we cannot actually send this across threads. So earlier when we had this error coming out of the compiler, we know that there was a function somewhere along the way which actually dealt with sending data across threads, and that would say I only work with types that implement send. Kind of that was the one point that says I need send to actually send this across a thread. And so that's where this trait bound is coming into play, and kind of internally once you have that RCO string, you'll get forbidden at that point. But we also have this type called arc, which stands for atomic reference counting, kind of the dual of RC, only the atomic version. This is indeed safe to send across threads because the reference count is managed atomically, and then the internals, the actual string itself, is also thread safe. It's fine to send across threads. So this memcopy aspect is a little different than the send aspect, where it's kind of more of a property of kind of what you can do in moving the type and kind of how you create new versions of it, where integers or floats are kind of these primitives that are just a bag of bits. It's totally fine to kind of create new versions of that and kind of memcopy that all over the place. Types like string, though, or RC of string, if we're creating a new version of this, then we actually need to run some code. If we're creating a new string, we actually need to make a new heap allocation and kind of copy all the data onto there. If we're creating a new RC, we actually have to bump the reference count. We have to actually run some code to do that. And so this is where you can't necessarily memcopy all types in Rust because it's kind of creating multiple pieces of data that would be aliasing kind of new owners, but that's kind of violating this aspect of no aliasing when you have ownership, which only allows mutation. So all right, that's a little bit about traits. And now I want to talk about parallelism and kind of how we're putting traits and borrowing kind of all this together to build up these parallelism aspects of Rust and kind of how we're freeing ourselves from these data races. And the key thing to know about Rust is that Rust did used to have actually channels baked into the language and kind of these various paradigms baked directly in here. But today in Rust, all the concurrency and parallelism libraries are external to the language, kind of in the crates ecosystem, in the standard library itself. And this is how these are all built on these fundamental tenets of ownership and borrowing and leveraging these along with traits for safety. But we're only ever actually using these at the library layer. We can kind of define them in Rust itself. We don't have to worry about the language providing intrinsics or primitives necessary there for that. And so the key thing to know about data races, which we're kind of all about preventing, is it has these three ingredients: this sharing, this mutation, and no ordering. And two of these sound very familiar at this point, where Rust is all about preventing aliasing, preventing mutation from happening at the same time. And so for free, we're effectively getting no data races in Rust. By preventing both of these from happening, we're forbidding one of these two ingredients from a data race happening, and so kind of we never have any data races in Rust. And this is kind of one of the things that kind of gives you this sense of empowerment of concurrent code in Rust and kind of how it almost always works on the first try. So I want to go through a quick example here of quicksort and kind of how you might implement a parallel quicksort in Rust using a crate called Rayon in the ecosystem. So I'll kind of skip the base cases, but so we have this bracket, which you haven't seen before, and that's a slice, kind of a list. This is a borrowed reference to a slice of integers, so someone else owns it, but we know that we have a chunk of memory that we can actually mutate and kind of modify all the internals of. We'll skip the base cases because that's kind of just how you implement quicksort, but the first time it gets interesting is this split at mute, where if we take a look at the standard library, what this is going to do is give us two halves. We have this pivot, which we're going to split the array on, and we want to make sure that we get two halves here and kind of work on them in parallel. It's kind of our overall goal and overall how quicksort is implemented. If we take a look at the standard library, this is the actual signature of the split at mute function. And so we'll notice, okay, we have these lifetime parameters. We're kind of connecting the lifetime of the first slice to the outer two slices, kind of the left and the right. And we'll kind of make sure the lifetimes are ending here. So the vec itself is transferring itself. The lifetime of the vec is being transferred to the pair being returned. And then that lifetime is going to go out of scope when the function actually returns. But one of the key aspects for safety here is that we're transferring this, we're transferring the usability of this vec, kind of this input vector, to these two subslices. Because we'll notice here, if we actually had access to vec less and greater, then we have this aliasing. They're all mutable, but the vec is aliasing both less and greater. And so what's actually happening here is that you're effectively moving this value. You are moving the mutable reference of vec into the split at mute function, which is then giving you back ownership, but in two halves, kind of giving you two unaliased versions. And the critical thing here is that when we use this crate, which is actually going to do this in parallel and kind of run these on two separate threads, or kind of an efficient aspect, we know that this is safe to do because both this less and this greater are not aliasing. Kind of, although they are mutable, they're not actually aliasing, and so there's no possible data race to come up here because each of these recursive calls to quicksort will kind of be touching the internals, but only in the one contained slice that it has, kind of in two disjoint locations. And so this join function in the Rayon crate, that's defined in the ecosystem. It's not in the standard library. It has various knobs for kind of dealing with how you deal with thread pools and how you deal with work stealing and whatnot. But effectively, it's going to take these two closures. That's kind of this like double bar here. Up there is a closure syntax saying we're now introducing a closure in Rust. And so one closure is qsort on the left, one closure is qsort on the right. I'll be executing these in parallel and then waiting until they're actually both finished. And so this function will only return once the left and the right have both been sorted at this point. All right, so the next thing we saw in the Rayon crate from earlier was this parallel iterator aspect, which is saying that we can not only iterate over a list sequentially, but we can also do it in parallel on a bunch of threads at the same time. Now notice that once we create a parallel iterator, it's giving us all these nice things we saw before, like with the zip, this map, and this sum, kind of all these aspects you'll expect from the standard iterator trait is also being given to you by the Rayon crate and kind of happening all parallel at that point. And the way this is actually implemented is there's this trait kind of representing all parallel iterators, which is very similar to the iterator trait itself, but it's all built internally on this one join function. We have this kind of one fundamental primitive, which is kind of doing both things in parallel, but maybe on separate threads. And so that's effectively what's happening here is Rayon is using this one primitive to kind of build up all these extra primitives. And you'll see this is kind of a very common pattern in Rust where we kind of use one core primitive to start building up all of these extra abstractions on top of it. And so this is not the same table as before. We have kind of concurrency paradigms here as opposed to the aliasing and mutation. But you'll find we've been talking about fork join parallelism, which is kind of leveraging this borrowing, leveraging this aspect of making sure the lifetimes work out to make sure you have disjoint slices, you're not using them after the wrong time, and kind of everything is safe to send across threads and whatnot. But you'll find a bunch of other paradigms, which I was talking a lot about yesterday as well, such as message passing, locking, lock-free data structures, futures, kind of all these aspects, which end up leveraging the ownership and the borrowing and the various traits here to kind of make sure this all builds up into one nice, usable, and safe package. So, all right, the next to last thing about the language that I want to talk about is unsafe. This is kind of the dark underbelly of Rust, kind of how you actually end up implementing a lot of these aspects. And so when we originally created Rust, we wanted to make sure that it was an extensible language, that you can kind of go outside of the language. We're not decreeing that you can only do a particular kind of subset of functionality, but you can kind of do whatever you like as long as it eventually fits into our nice subset. So the core language, as we've been seeing, has ownership and borrowing, and libraries are also going to be adding things like reference counting or files or parallel execution. And it's not clear how we're going to map reference counting onto just ownership and borrowing. I was saying that we only allow either aliasing or mutation, but reference counting is kind of this own value, but also shared. So it's both ownership and kind of some aliasing going on there. And files are having to interoperate with the OS. Threads the compiler doesn't even know about. And so I want to show you how these are both implemented and then how we end up making them safe a little bit later on, kind of how these will internally be using the ownership and borrowing at the outer layers, but internally they're using this thing called unsafe. In Rust, we have these blocks called unsafe blocks, which kind of give you extra powers once you're inside of them. So the type checker is still turned on, you still have borrow checking, you still have kind of all the other safety checks in Rust, but you can do a few extra things which are normally very, very unsafe to do. And so the reason that the safety in Rust doesn't break down and everything isn't terrible at this point is that you're kind of telling the compiler, trust me, I know what I'm doing. I'm actually putting this in a safe interface. I'm actually giving you a safe abstraction on top of this, and that's the one that's actually going to do some validation. So for example, the split at mute function we were looking at, that took this index and a slice to kind of split the slice on. What's actually happening is that's asserting that it's actually in bounds, actually within the range of that slice. And then after we've passed that assert, we now know that this is a valid actual function call, and then internally we're going to have to do some little unsafe pieces to actually split that mutable slice into two disjoint different slices. And so some of you might be thinking, well, that all sounds great. You can have a nice safe interface whenever, but what if everyone just tries and uses unsafe everywhere? Like, what's actually stopping you from using unsafe and then kind of putting this unsafe boundary everywhere in your code base? And so this is a tweet by one of the Servo developers. This is a web browser written in Rust, which did an analysis of the Rust code that was actually released today in Firefox 57. And they found that their 35% of their code was indeed unsafe, which is actually quite worrisome. So when you actually look into it, they have about 70,000 lines of code they wrote, and then 70,000 lines of code that's kind of mundane, talking to C++, generated code, various stuff that's kind of very straightforward. And the key thing to notice here is that of the code they actually wrote, less than 2% was unsafe. And this is kind of showing off that even in large code bases, even in very, very large Rust code bases, you have a vanishingly small fraction of actually unsafe pieces of code. This greatly limits the code that you need to audit, the code that you need to be very careful about when you're editing. It kind of gives it a nice little container. And now talking to the actual system, kind of talking to C++, talking to the OS, kind of talking to all those aspects, that is indeed unsafe. But it tends to be relatively straightforward and verified via other means, and so there's you do have to worry at that point. But even this 35% number is not as worrisome as it originally looks. And so the last thing that I want to talk about with unsafety is that the reason this ends up not being a problem for everyone is kind of this aspect of layering, this aspect of building on existing abstractions. So in the Rayon crate, we saw we have parallel iterators, and it turns out that's all almost entirely safe. There's no unsafe blocks anywhere internally, and that's all built entirely on this join function, which itself is safe. And then we're just using standard ownership and borrowing and never using the unsafe keyword anywhere inside these iterators. Now, join function, however, does have this safe interface, and you cannot call it incorrectly, or kind of you will always get a compile time error. Otherwise, it does have unsafe internals. To actually execute those two closures on both threads and kind of fork that out there and kind of make sure that it doesn't return until both of them have actually finished, that's a little bit unsafe, and you have to have some unsafe blocks to actually delegate that out. And finally, the literal thread pool, which is running all these closures that have borrows all over the place and have to be scheduled just right, that's almost entirely unsafe. But we can see here that this body of code is getting smaller and smaller. And so the thread pool is where you focus all your attention in terms of reviewing and auditing and looking very closely when you modify it, and kind of as a warning for new contributors, a warning for someone just coming in. You got to be really careful looking at this and kind of have some extra scrutiny later on. Oh, and the final thing that I'd like to talk about is the crossbeam crate, which is another crate on crates.io for kind of dealing with concurrent data structures. It's kind of giving you this scheme for kind of like GC, but not quite for writing some data structures in Rust. And it's quoted as being partially safe or almost safe, where it has this one API that is indeed unsafe. But the reason it's actually used quite a bit and it doesn't all just fall down and have no safety guarantees at all is that it's clearly documented why it's unsafe. You clearly know what the criterion are to actually make this safe. How do I actually call this function and make it safe? And so this is very similar to C and C++, where in theory, every function is documented with how to actually make it safe. But in Rust, you tend to also have, because unsafe is used so rarely, you'll have very clear contracts here saying, oh, you have to make sure to call this function at the right time, or you can't call this function before you call this function. And then it's relatively easy to actually adhere to those guidelines and actually productively use crates like Crossbeam. Yeah, the library will end up handling a lot of the extra stuff for us. So all right, that's a little bit about Rust and a little bit about the kind of parallelism and trait aspects. Before I go on, does anyone have any questions? Yeah, I'm going to repeat it so it's fine. Right. So the question is kind of how do we deal with control flow branches and ownership? So if you have an if statement and you initialize it on one, what happens on the other and stuff like that? And the answer is that we do actually have control flow analysis and all this. And so if you have a local variable and you initialize it in one branch of an if, you still can't use that local variable afterwards if you didn't initialize it in the other branch. And so every single path of code has to have an initialized value, has to actually initialize that and continue using that at that point. And similarly, if you move on one branch of an if, so I have a local vector and I say like if something, move it, else, blah, 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 you can't use it after the if because it may have been moved and so you can no longer have access to that. So it's one where like effectively you will statically make sure that on certain branches you can or cannot be using these own values. So to reword this kind of like if you have an existing structure and then you modify some fields, what prevents it from to still be working at that point, where it maybe switches from copy to not copy? Right. So the question is, can you implement copy for string, for example, or some type that cannot be copied? And the answer is no. The copy trait is a little bit special in Rust, where there is an assertion saying that if you're an aggregate, like a thing that has two strings in it, then you cannot implement copy for that because the strings themselves do not implement copy. So you have a compiler verified implementation saying, oh, I cannot copy this because there are some fields that can't be copied. And kind of, if it were only integers internally, then you could actually implement copy. That's actually valid to do at that point. Yeah. And you had a question? Sounds good. Excellent. All right, so I'll have some more time with you again, but I want to get through this as well, so don't worry, we'll get to this. So the next thing I want to talk about is a bit of a success story for Rust, which actually culminated literally today with Firefox 57 being shipped. And so this was kind of Rust being shipped in a production code base in a giant C and C++ code base. And so the problem here stems from this fact that we have this giant style system, which if you don't know much about this, I also don't know much about this, but in any case, we have this kind of, this is what the browser is doing, kind of your web browser, when you download a web page. You'll kind of parse the HTML page, you'll make this giant tree of you have your HTML node, your body node, your div nodes, kind of everything internally. And what's going to happen is that the browser now needs to compute some list of styles for every single node here. So every single one of these nodes is going to need this kind of computed styles of how big is this, what color is this, how much padding do I have, my margin. And this is kind of the CSS aspect where what we're going to be doing is kind of filling in this giant table for every single node. But to actually calculate this value, we're going to be traveling up the tree. So if I don't list what my color is, then my parent might list that, or I will inherit that from their parent, and kind of like traveling all the trees to actually calculate every single one of these applications, or kind of every single one of these properties. But the key thing here is that this is kind of inherently what you have to do, but there's no reason that this needs to be done sequentially. This is actually relatively parallel. We kind of have this left-hand side of the tree and this right-hand side of the tree. You're kind of tons of leaves at the very bottom, and there's no reason for that to all be done on one thread. So I have bugs like this in which I showed yesterday and started off with which is we need to parallelize CSS selector matching, and this was opened 7 years ago. This bug opened on a C++ code base, just kind of sat there saying we have all these performance gains to get, but we can't actually quite do that because it's, I don't know, I'm sure many of you, I'm sure, is aware, it's very, very difficult to add threads to a C++ code base, to actually go and retroactively make sure that you don't have steg faults, you don't have data races, you free everything correctly and all that. But what Rust really did is they were using that superpower. They were using that extra spinach, that Popeye spinach, and getting these nice graphs saying that we now have a parallel CSS rendering engine written in Rust, and it's all kind of using all the cores you have available, and we're immediately getting these great speedups on certain websites. So we have the page layout aspect is actually decreased quite dramatically in some cases and kind of is only limited by Amdahl's law at this point. Now, internally, we have a bunch of other stuff to optimize to get your page rendering time to literally 0, but that'll take a while. So this is kind of a great example of how this actually shipped today, like literally today, and is now available in Firefox in production, and is an example of taking Rust into an existing C and C++ code base, kind of that whole idea of gradual adoption, kind of like you don't have to rewrite overnight in Rust. You can kind of get the benefits in a very localized fashion. So this is one of the cartoons which has been using to describe this aspect of what we call Quantum, which is kind of this release of Firefox right now. And you'll notice that 2 of these components are currently written or being written in Rust, the kind of this CSS engine we were talking about, and soon the renderer, kind of what actually puts pixels on the page and touches the GPU and all that, is going to be written in Rust and kind of taking advantage of that parallelism aspect and kind of using all those safety guarantees. But at the same time, all the extra stuff being written in Firefox, kind of these new components are also being rewritten in C++ or freshly written in C++. And all of these aspects of the system are kind of interoperating together and kind of working seamlessly together. And this is kind of where Rust as a systems language works very well in embedding into existing applications. There's no runtime, you don't have to worry about a garbage collector and all that aspect. So the last thing I want to talk about before I get to a few more questions is the community aspect of Rust. And kind of this is one which is easy to overlook, but ends up being one of the most important aspects of Rust and kind of the most important ways of how we have gotten to where we are today. And the first thing you'll notice about the Rust community is it's incredibly open and welcoming. This is an excellent author, Julia Evans, who had a blog post where she was talking about how she just wanted to kind of play around with some kernel aspects in Rust and kind of, she wants to write a keyboard driver, and it turns out that the #Rust IRC channel, there was already tons of people, even though it's only tangentially related to Rust, were there and ready to help her. And this is kind of not only Rust questions, but kind of any various coding related questions. You'll find this very open and inclusive and welcoming community you'll find on IRC channels, on forums, on our subreddit, kind of all these places you feel the sense of Rust and it kind of makes you feel comfortable, at least in kind of in terms of working with Rust and working in the community and kind of feeling a part of feel like being a part of all that. And the other thing we have right now is we kind of did this planning process at the end of 2016 and created this 2017 roadmap for Rust, which is kind of mapping out the community's goals for where we want Rust to go in 2017. What are the highline items that we have to finish by the end of 2017? And during the last 3 months here, we kind of did a lot of planning the first 9 months. The last 3 months of this year, we've created this impl period, this idea that we're kind of splitting up into 40 different teams across the ecosystem. And these are all kind of working independently on various aspects of this roadmap, kind of all at the same time working towards the same goal, which is the 2017 roadmap in Rust. And so this is a great embodiment of how community participation and kind of engaging the community and leveraging the resources we have in the entire Rust community is a core tenet of Rust and something that we're constantly trying to capitalize on. And so if you're someone who's getting interested in Rust, this is actually a perfect time to jump in and to actually kind of work with Rust and kind of see what's going on and to start contributing to the compiler, the libraries, the ecosystem, kind of all of these various aspects have some working group related to them. And the last thing I want to talk about is the RFC process. And this is kind of the process by which we actually change Rust. RFC here stands for request for comment and is a way through which people can actually propose changes to the language. Now, this is not only kind of contributors, but we as core team members or we as members of the project, we also go through this process. This is the only way by which you can actually change the Rust language, is proposing an RFC. And one of the great examples of this is these 2 RFCs were actually proposed by a community contributor, where we took a look at these. We're like, unions, we don't need those. We have other stuff, can work around it for now. Or variadic functions, there's no need for that. Like we're going to do that later. But the community here ended up convincing us that this actually is very high priority and we do actually need to tackle these kinds of problems. And so these are 2 RFCs which we have since merged and actually implemented and stabilized unions, and were purely driven by the community and purely driven and brought to our attention and kind of and went through like that. So, all right, that's all I have for Rust. There's a couple of links here. The book is kind of one of the best places to get started if you're brand new to Rust. We have forums at users.rustling.org. We have a couple of IRC channels as well. And some the intorust.com is also some videos if you want to see some more introductory videos in Rust, very similar to this talk, but also some more in-depth talks. Other than that, if there's any more questions as well. Yes.
I noticed, sorry for the latency on this question, but it's regarding the parallel quicksort. Rust is saving me from actually sharing data between threads, but it's not saving me from false sharing data between threads. If I split and that split is not on a cache line boundary, then I'm going to be, have a cache line ping-ponging back and forth between cores. Is
Correct.
there anything in Rust that helps me with that problem, or do I have to figure it out myself?
No, this is one of those that's more related to performance rather than kind of the safety aspect, where there's not, in theory, there's no memory safety. Like, we'll expect that ARM needs to be aligned, so that's aligned and everything. But otherwise, you will have to kind of make your own abstractions for this. So you can write a type that's kind of like overly aligned, and you only sort overly aligned versions of that type or something like that. But that's, in general, for those kinds of performance optimizations, you still have to go out of your way, kind of like in C and C++.
Okay, and one second question. I know in C++ it's being discussed whether we have the notion of different kinds of RAM, right? Like RAM domains. Is there something like this in Rust at the moment? Like,
So I have never even heard of that. So the answer is no.
okay.
I suspect that a lot of Rust is driven by development in C++ and existing kind of seeing what existing applications are doing, and like most of Rust, the language is drawn from existing experience in other languages. I mean, ownership and borrowing, kind of the novel concepts in Rust, but almost everything else we're trying to pile on top of that. So this is something where we've ended up following a lot of aspects here. Like we drew async await very recently and drew a lot of inspiration from the coroutines TS for C++. And I suspect if we get shared memory spaces or multiple memory spaces, we'd probably find a similar solution for Rust. But baked in right now, not so much.
Okay, cool, thanks. I wanted a copy from you.
Yes. Now you have to wait for a microphone.
So what about compile time? How long is this engine for CSS, for example?
Right. So I gave this answer yesterday. My current answer is it's really bad. But the nuance there is it's fundamentally much faster than C++. And I'll give the detailed answer here, which is that right now the unit of compilation in Rust is a crate. So an entire library, which means that when you edit code, you're recompiling an entire library all at once. Now, I was saying we have monomorphization, which is kind of creating multiple copies of functions, and that's why an entire library ends up having the compile time kind of on order of C++ if you compile it from scratch. So what ends up happening is that if you compile roughly equivalent C++ and roughly equivalent Rust code at the same time from scratch, Rust in theory is much faster. We have that type checking model with generics and with traits saying we only check it once. We never check it every single time, just that one time. So the only exponential blow up here is the cogen, which is the same as C++ and ends up being much faster. Now, on the other hand, the incremental compile times here are much, much worse, where today, when you change a crate, you have to recompile the whole crate and then do that down the chain, whereas in C++, you recompile the one file and then you relink and you're done. So it's kind of on the order of just that one file you're modifying. And so the caveat here for why it's going to get much faster in Rust is that we're currently developing incremental compilation for Rust itself. This is something that's kind of baked directly in the compiler, where it has all these cached and saved pieces, where currently it's incremental in terms of cogen, where we'll kind of take your crate, we'll automatically split it up into a bunch of object files, and we'll just only regenerate the ones that you modified, or the ones that actually need to be touched. And so we'll save all that information, but we're going even further than this as well. We're going to start caching and having incremental type checking, so you don't actually need to type check the entire crate as well. If you change the internals of a function, there's no need to re-type check everyone who called your function, for example. So this has been under development for quite some time now, and is showing some massive, massive wins in terms of compile time, and is what actually gets you far, far closer to the incremental compile time of C++. So the long-winded answer is that literally today, on stable Rust, an incremental compile time is slower than C++, very much so, because you're compiling entire libraries. Full compiles end up being a little faster, and tomorrow, full compiles will still be faster and will likely be faster than C++ in terms of we have more incrementality available to us, both type checking and cogen.
I think we can take one more question.
Okay, we have question here.
I just realized there's like this whole section of audience that's just blinding, and so I can't see you. So if your hand was up, sorry about that. But yes.
What does the glue look like between Rust and C++?
A very good question. And the answer is nothing. The answer is it looks exactly like C, where when you call a foreign function from Rust, so you call strlen, for example, it's literally just call strlen in the assembly. There's nothing fancy going on there. It's exactly as if you called it from C. And similarly, you can expose a C ABI in Rust. So you can define a strlen function in Rust, which is directly callable from C and C++. There's no need for kind of extra runtime aspect going on there.
So I can't pass either language's vector back and forth or anything like that.
Correct. Rust does not have a stable ABI. Rust does not have any sort of stability in the standard library types and the options, the results, the enums, kind of everything there, entirely unstable. So we have this notion of FFI safe types. So integers are FFI safe. Like you can share the raw pointers and the references and things like that. But in general, we can't take a C++ vector and we can't hand a Rust vector to C++, for example.
Thank you for the talk.
Thank you.